moment of the initial explosion marked the beginning of the universe. As light and matter danced, the universe expanded endlessly. With the birth of galaxies and stars, planets sprouted the buds of life, infusing vitality into the universe. But is there no end to the expansion of the universe? After inflation ends, the universe welcomes the cycle of contraction. Finally, the universe will return to the moment of departure, to the moment when the Big Bang exploded. The cycle of the universe is not eternal. The evolution and destiny of the universe, a story yet to be told. Scientists leave predictions and hypotheses, leaving questions about the future of the universe. The hypothesis of a universe that expands and exists forever. The imagination of the Big Crunch, which contracts again and meets the end. The mystery of the universe, a riddle yet to be solved. It's a big topic that we can't understand, but the universe gives endless inspiration and brings us beautiful stories. Today, we want to discuss the evolution and destined end of the universe in the 5th session of Introduction to Cosmology. Subscriptions and likes are a great help in video production. In The Grand Design, Dr. Stephen Hawking explains the birth and evolution of the universe as follows. The origin of the universe can be explained by the Big Bang theory, which postulates that the universe began to expand explosively from an extremely hot and dense point about 13.7 billion years ago. During this expansion, the fundamental structure and laws of the universe were determined. The evolution of the universe is governed by its initial conditions and natural laws. The initial state of the universe is a result of chance, and natural laws regulate the development and changes in the universe. The universe we inhabit is just one of many possible universes, and other universes may exist. Scientific explanations for the origin and evolution of the universe do not require divine intervention. The universe can naturally arise and evolve, and all phenomena in the universe can be explained by the laws of physics. There is no need for a designer of the universe, and answers to fundamental questions about the universe can be found through scientific methodology. The universe we live in has evolved through various physical laws. For example, some of these laws include Newton's laws of motion, describing how the motion of objects changes based on the forces acting on them, and how force and momentum are conserved among interacting objects. These laws explain phenomena such as planets orbiting the sun, satellites orbiting the Earth, and us throwing and catching objects. Theory of relativity, explaining how space-time is curved by matter and energy, affecting the motion of objects, with implications for phenomena like black holes, gravitational waves, and the dilation of time. This theory explains that the speed of light is always constant, and as the speed of an object approaches light, its mass and time change. This theory also explains phenomena such as black holes, gravitational waves, and the passage of time. Quantum mechanics, describing the behavior and interactions of particles in the microscopic world, where motion is probabilistic and uncertain, and observations influence the system. This theory explains phenomena such as atoms, molecules, electrons, photons, lasers, superconductivity, and quantum computers. In addition to these, there are other physical laws like thermodynamics, electromagnetism, nuclear forces, and the Standard Model, contributing to the understanding of the structure and changes in the universe. Dr. Stephen Hawking foresees and warns about the fate and end of the universe as follows. The universe could end in a big crunch, where the expansion halts and reverses, causing all matter and energy to contract into a single point. At this point, all physical laws become invalid and time ceases. The universe could end in a big rip where the expansion accelerates, causing all matter and energy to become increasingly sparse, eventually leading to the disintegration of atoms. The universe would end in extremely low temperature and high entropy. The universe could end in a big freeze, where the accelerated expansion causes all matter and energy to drift apart, leading to the disappearance of stars and planets, leaving only black holes. The universe would end in a dark and lonely state. These predictions about the fate and end of the universe may vary based on current physics theories and the initial conditions of the universe. The destiny and end of the universe are also linked to the fate and end of humanity. Dr. Hawking asserts that to survive potential cosmic crises, humanity must find ways to leave Earth and inhabit other planets or stars. Quantum gravity theory is a field in physics that aims to describe gravity in quantum mechanical terms. Gravity is a force associated with the large-scale structure and phenomena of the universe, explained by general relativity. In contrast, quantum mechanics is a theory that describes forces and behaviors on the microscopic scale, such as atoms and particles. While both theories have been highly successful in their respective domains, unifying them poses a formidable challenge. Quantum gravity theory attempts to merge these two theories and understand gravity in extreme situations, like black holes or the Big Bang. Quantum gravity theory is still incomplete, and various contenders have been proposed. One of the most well-known candidates is string theory. String theory represents all matter and forces as vibrating strings in a one-dimensional framework. It seeks to unify all four fundamental forces, including gravity, within a single framework, and expands the dimensions of the universe to 10. Another prominent contender is loop quantum gravity theory. This theory represents the smallest units forming spacetime as loop structures. Loop quantum gravity theory separates gravity from other forces, abandons the continuity of spacetime, and sets the Planck length as the minimum length. Quantum gravity theory is a crucial area of research for finding answers to fundamental questions in physics. However, due to the mathematical complexity of the theories and the challenges in experimental verification, many mysteries and puzzles remain. The development of quantum gravity theory holds the promise of providing a deeper understanding of the origin and structure of the universe, the interiors of black holes, and the unification of physical laws. Brain world and M-theory are forms of the multiverse hypothesis, evolving from string theory. Brain world suggests viewing our three-dimensional universe as a floating membrane, brain, in higher dimensional space. These brains can collide, separate, or bend, creating various universes. M-theory extends string theory to explain such brain worlds, expanding the universe's dimensions to 11. M-theory aims to unify the four fundamental forces, including gravity, into a single framework, offering a deeper understanding of the universe's origin, structure, black hole interiors, and the unification of physical laws. The ultimate theory, or theory of everything, seeks to integrate and explain all forces and matter in the universe with a single equation. This theory could provide answers to the origin and structure of the universe, the internals of black holes, the possibility of time travel, and the existence of the multiverse. Dr. Hawking dedicated his lifetime to finding this theory. He discovered Hawking radiation from black holes and researched the thermodynamics and information theory of black holes. Additionally, he attempted to explain the universe's origin and structure through brain world and M-theory. In his book, The Grand Design, he argued against the notion that a deity created the universe, asserting that the universe can naturally originate and evolve, with all phenomena explained by physical laws. Dr. Hawking acknowledged the challenges physicists face in finding the ultimate theory, but he believed that, at some point, humanity would unveil it. He expressed confidence that despite the obstacles, physicists would eventually reveal the theory of everything to the world. Space-time is a mathematical model that combines the three dimensions of space and one dimension of time into a unified four-dimensional continuum. Each point in space-time is referred to as an event and requires four numbers for its specification: 3 spatial coordinates, x, y, z, and 1 additional coordinate for time, t. The characteristics of space-time are dependent on the theory of relativity. The theory of relativity is a physics theory that explains the space-time structure of the universe and gravity. It is divided into special relativity and general relativity. Special relativity describes the characteristics of space-time in systems undergoing uniform motion without gravity. This theory explains that the speed of light is constant, and as an object's speed approaches that of light, mass and time undergo changes. Special relativity assumes space-time to be a flat and Euclidean space, often referred to as Minkowski space-time. General relativity, on the other hand, describes the characteristics of space-time in systems with non-uniform motion and gravity. This theory posits that the space-time of the universe is curved by matter and energy, and matter and energy move in response to the curvature of space-time. General relativity assumes space-time to be a curved, non-Euclidean space, often referred to as Riemannian space-time. The quantum nature of space-time refers to the quantum properties of time and space from the perspective of quantum mechanics. Quantum mechanics is a physics theory describing the behavior of matter and energy, acknowledging discrete quantum states and phenomena such as wave-particle duality. Quantum mechanics abandons the continuity of space-time, introducing the concept of Planck length and Planck time as the minimum length and time. Quantum mechanics predicts phenomena like space-time fluctuations, quantum foam, and loops. This detailed explanation provides insight into the characteristics of space-time, a fundamental concept in physics, aiding in the understanding of the structure and changes in the universe. Dark energy is an unknown form of energy that exerts the largest scale influence on the universe. The existence of dark energy was first suggested in 1998 when observations of supernovae revealed that the expansion of the universe is accelerating. Dark energy is a force with negative pressure that accelerates the expansion of the universe, offering a new perspective on the history and future of the cosmos. The properties and nature of dark energy have not been definitively established. The simplest model for dark energy is represented by a constant called the cosmological constant, which denotes the energy density of empty space. The cosmological constant is independent of time and space and is thought to be related to vacuum energy predicted by quantum mechanics. However, there exists an enormous discrepancy of about 120 orders of magnitude between the size of vacuum energy and the cosmological constant, known as the cosmological constant problem. Another possible model for dark energy involves a field known as a scalar field, represented by a single scalar value. Scalar fields can vary over time and space and can possess negative pressure. One type of scalar field, called quintessence, exhibits a characteristic of decreasing energy density with the expansion of the universe, similar to what was used in inflation. An attempt to explain dark energy involves modifying Einstein's general theory of relativity, referred to as modified gravity theories. Modified gravity introduces additional terms or dimensions into the equations of general relativity, creating an effect that accelerates the expansion of the universe. Quintessence is an example of modified gravity, exhibiting the property of increasing energy density with the expansion of the universe. Various methods are employed to measure dark energy, including techniques using galaxy distributions, baryon acoustic oscillations, gravitational lensing, and cosmic microwave background (CMB) radiation. These methods allow for the measurement of the expansion velocity and geometry of the universe, enabling the estimation of the equation of state of dark energy, which represents the ratio of dark energy's pressure to energy density. The future and cosmological implications of dark energy remain uncertain. Depending on the equation of state for dark energy, the fate of the universe can vary. For instance, if dark energy behaves like a cosmological constant, the universe will infinitely expand and cool, known as the Big Freeze. If dark energy behaves like quintessence, the universe will rapidly expand, eventually destroying all matter and energy, termed the Big Rip. Dark energy could serve as a crucial clue in the quest for a theory of quantum gravity, integrating quantum mechanics and general relativity. Dark energy could serve as a crucial clue in the quest for a theory of quantum gravity, integrating quantum mechanics and general relativity. This time, we explained in detail the dark energy that continues the evolution of the universe. Dark energy is one of the most important and interesting topics in cosmology and astronomy. The cosmological constant was originally introduced by Einstein in his general theory of relativity to explain a static universe. But he later withdrew the concept when it became evident that the universe is expanding. However, with the discovery of evidence indicating the acceleration of the universe's expansion in 1998, the cosmological constant was reinterpreted as a new form of energy known as dark energy. The cosmological constant, now considered a form of dark energy, is a force sustaining the expansion of the universe, offering a novel perspective on the history and future of the cosmos. Additionally, the cosmological constant could serve as a crucial clue in the quest for a theory of quantum gravity, aiming to integrate quantum mechanics and general relativity. Now, let's delve into the explanation of whether the space in the universe is filled with dark matter. It is correct that the space in the universe is not empty. Rather, it contains various forms of matter and energy. The cosmic space is filled with visible matter, such as stars, planets, and galaxies, along with invisible substances like cosmic microwave background radiation, neutrinos, chemical elements, and cosmic dust. However, these visible and invisible components collectively make up only about 5% of the total mass and energy content of the universe. The remaining 95% is composed of dark matter and dark energy. Dark matter constitutes approximately 27% of the universe and appears to be a form of matter that does not interact with light or other electromagnetic radiation. Although dark matter cannot be directly observed or measured, its presence indirectly influences the structure and dynamics of the universe through gravity. For example, the rotation speeds of galaxies, galaxy clusters, gravitational lensing phenomena, and the large-scale structure of the universe provide indirect evidence of the existence of dark matter. The specific particles making up dark matter remain unidentified. Various candidates, including quarks, neutrinos, axions, WIMPs, weakly interacting massive particles, have been proposed, but conclusive evidence is still lacking. Several experiments are underway to detect and study dark matter, but successful results have not yet been achieved. While dark matter fills the space in the universe, its density is extremely low. The average density of dark matter is on the order of approximately 10^27 kg m3, similar to the average density of the universe. However, dark matter is not uniformly distributed. It tends to be more concentrated in regions such as galaxies and galaxy clusters. Dark matter is found to be more prevalent in the outer regions rather than the central regions of galaxies, constituting the majority of a galaxy's mass. This explanation provides insights into the presence of dark matter in the vast cosmic expanse, offering a glimpse into the mysteries and beauty of the universe. The birth of the universe began with the Big Bang, its evolution shaped by the forces of gravity, dark matter, and dark energy, filled with galaxies, planets, stars, and black holes. The universe's mysteries explored through physics, astronomy, mathematics, and philosophy. How will the universe meet its end? Will it halt its expansion and contract into a big crunch? Or will the expansion accelerate, leading to a big freeze? Perhaps a faster expansion, resulting in cosmic destruction and a big rip? The destiny of the universe remains unknown, but its beauty is there for contemplation. The exploration of the cosmos can continue. The cosmic poem will endure without cessation.